Okay, so good afternoon, everybody. I hope you did enjoy your lunch and you are not too tired to listen to this last session of the Global Sustainable Aviation track. And this session will be focused on maybe something different compared to all the other presentations that you had followed during this event. It's about airspace and operational efficiency. But first of all, I would like to introduce myself. I'm Marilyn Bastin, the Acting Director for the European Green Sky in Eurocontrol. I'm leading innovation and research, aviation intelligence, and also aviation intelligence. For those who don't know Eurocontrol, Eurocontrol is an intergovernmental civil-military organization with a mission to support the European aviation. We are working with 42 member states, with Airspace, with airports, with airlines, with EU institutions to make the European air traffic management more efficient. And so we are also called the network manager. And now for this session, you know, I'm used to say that the best emissions are the ones that are not emitted at all. And during the presentation in the morning, you saw different figures about ATM. And actually, if we want to be more efficient from a sustainability point of view, we need to reduce our emissions. And how to do it? It's by being more efficient from an airspace and operational efficiency. And it's what our speakers are going to speak about today. And we will better understand how innovation and new technology and artificial intelligence, for instance, could support the optimization of our airspace and operation. And as I say also, there is one benefit with this airspace and operational efficiency. It can be implemented now on short term. And it's why it's important that we are working on this, even if the number is lower than the other dimension to decarbonize the aviation sector. And now I would like to invite our first speaker, because I don't want to speak too much. You are here not to listen to me, but to listen to them. So I would like to invite Mr. Akbar Sultan, who is the Director of the Airspace Operations and Safety Program at NASA's Aeronautics Research Mission Directorate. He is responsible for senior executive leadership of NASA's research portfolio across 4 NASA research centers for current and emergence users. And with his presentation called NASA Sustainable Flight National Partnership Operations Research, we will know more about how we can make one sky for all users. So Akbar, please, the floor is yours.
Thank you for the kind introduction, and thank you for being here. And it's a great day at ICAS to be speaking with all the distinguished fellow researchers here. I mean, I'm just walking around the building and everything else, and I just can feel the brain power. It just gives me like quite a lot of comfort. So I'll talk briefly about NASA's efforts on sustainability, because we do quite a bit of work on sustainability, both from the operations side and, of course, vehicle side. And I think earlier this week, you've also heard some additional NASA work that was presented where they're developing new engines, new airframes, and new capabilities and hybrid electric concepts and various other ones, trying to drive the vehicle sustainability. My focus is going to be on operations and safety. So if we start looking at the future of aviation, we can see that the future is changing quite a bit. It's no longer going to be the same idea of, regular tube and wing aircraft all operating within Mach 0.001 of each other, and a few GA and helicopter thrown in. There's going to be quite more variety of vehicles, whether it's the low altitude UAS airspace, advanced air mobility, large HALs operating at above 50,000 feet, supersonic aircraft operating at above 50,000 feet, and or, of course, this, space launches occurring. So this changing dynamic forces us to start looking at sustainability in a different way. We can't essentially, as Associate Administrator Pierce earlier this morning talked about, we can't efficiency our way into it. We can't do an incremental change. We have to look at the whole system in order to be successful. So as we look over the future, it's going to be driven by three things. Diversity, the diversity of vehicle and their performance and their emissions. And what I mean by that is, you have your tubing wings, you have UASs, autonomous, advanced air mobility, HALEs, all these other types. Performance. You could see a vehicle at above 50,000 K, a HALE operating at about 15 knots, occupying the same airspace as a supersonic going at above Mach 1.5. I think you could all agree that would be a problem. We have to do something about it. We have to approach airspace management in a different way. And the missions are going to be different. They're no longer going to be airport missions. You could have vertiport to airport missions, vertiport to vertiport, rooftop to rooftop. You get the idea. The density of operations is going to go from the current about 10,000 operations, tens of thousands of operations to millions. In the United States, our daily operations are, for commercial transports, is about 50 to 70,000 operations a day on a daily basis. But as you start looking at UAS and advanced air mobility, that's going to go to millions. And that makes things a lot more complex as well. New operations, airspace interoperability. So therefore, if we want to do sustainability and we want to do safety, you have to fundamentally transform the airspace. We have to move from the current human-centric approach to assisting the human with additional automation and autonomy, because the human just will not have the sufficient bandwidth or the reaction time. I'm not at all, let me just be very clear, we're not advocating human replacement. That's not what NASA is about. It's about assistance to the human via additional automation. So we are approaching things collectively, jointly with FAA, in terms of moving from the current next-gen environment to a middle phase of about 2035, 2040 timeframe, where we're going to move towards what we call service-oriented, tailored mission-oriented services, and some predictive risk management. But in what I talked about in the previous chart of going to that very highly automated environment, this is where NASA Sky for All vision comes in. And Marilyn, I like the way you said it earlier in terms of Sky for All in your opening comment, where we want to have additional complexity, scalability, and dynamic adaptation of the system through automated means. And for safety, in order to maintain the current safety and or enhance it, we have to go to predictive proactive safety. What that means is using data analytics and ML/AI to be able to identify threats and things brewing in the system before they have an opportunity to actually become an incident or an accident. So that's what I mean by proactive predictive risk management. And we've already made some headway in those areas. So that's our vision of moving towards this future transformation for sustainability. Now, given the vision, visions are always good, but as researchers, and of course as my colleague from Lufthansa probably will ask, well, visions are wonderful. Now, reality is better, right? So we're trying to do real stuff too, in addition to it. So this is now, we'll talk about some real impacts. We are embarking on a set of 4 operational validation and evaluation for benefits assessment of our technologies jointly with industry and FAA. Starting with initially with departure rerouting ground weather, building it up to inter-FIR oceanic flow management for sustainability, because you've seen the ICAO 2050 zero net emissions vision statements, and almost close to 50% of the aviation CO2 is mainly in the oceanic long-haul flights. So being able to make a difference there and impact, that would be a huge impact for us to be able to have. We're going to build that up to integrated flight deck and ground-based integration, and then concluding with disruption management. In the disruption management, the initial use case that we'll be focused on is rerouting and flow management around space access and space launch. Because I think we both can agree, both on the US side and the European side and everywhere else in the world, that the space launches and the disruptions it causes to commercial transport, it causes a lot of unnecessary CO2 burn with delays. Now, if we can do a better way of being able to predict what the debris field of that launch is, and to be able to do dynamic TFRs, temporary flight restrictions, that allows the airspace to be dynamically opened up will allow far more flexibility, and that's what the main focus of that final validation will be. Now, speaking on the first one, this is an active flight trial that's ongoing today at the Dallas-Fort Worth region in Texas, as well as the southern Texas region of Houston. We have 3 airports participating in running NASA technologies, Dallas-Fort Worth, Dallas Love Field in Dallas, and also Houston Intercontinental. And FAA facilities there are jointly involved. Now, there's many FAA facilities that have to involve. For example, if you look at just DFW, there's 2 towers, DFW, Dallas Love Field. You have the D10, they call it the TMA. In Europe, you call it TMA. In the US, we call it the TRACON. And then, of course, you have the Dallas-Fort Worth FIR, or we call it ARTSI. And the same thing goes with Houston. There's Houston ARTSI and FIR. There's the Houston TRACON and or TMA, and the Houston Tower. So as you can see, that alone is just 9 facilities. And we have several airlines that are partnered with us, mainly American, Southwest, and United, along with JetBlue and Delta. And Envoy Air is American's regional hub carrier. So essentially, they operate the American Eagle brand. And what they're participating is essentially every single flight that launches out of those airports is run through an automated NASA scheduling algorithm that currently is looking at rerouting around weather. So you see a picture here is, for example, that airport is in the middle. In the United States, when the FIRs, the TMAs are established, or the TRACONs, the flow out of that region goes out the sides of that box. And the flows in, the arrivals come in through the corners usually. That's the way our procedures work. So you see there's a weather cell sitting and blocking the eastern side, and where aircraft would normally exit. Now, what is the current method? The current method is when the weather blocks your exit gate, you push back from the gate and you go sit at the end of the runway for a ground hold, right? And you sit there until the weather clears, and hopefully by then you have not run out of fuel, idling the engine, or your pilot and crew has not timed out. And if that's still the case, they'll say, okay, now you can get prepared to depart at a certain time. And that could be, sometimes between 20 minutes to an hour plus. What this tool does, it does a full assessment. Does the vehicle have enough fuel? Does the crew have enough hours? And if I were to reroute you through a different departure gate, would you get there quicker than having to absorb the ground delay? And yes, that other route is longer. So there is, an additional fuel burned. But it also does a fuel offset. Does the additional fuel burned on the reroute, is that less than you absorbing a fuel due to the ground delay? And if so, it provides the dispatch a set of trajectory option sets, and it says, these are your available option sets. Here's the cost benefit of each one. You choose. The dispatcher will select one. They send it to the pilot via CPDLC and says, request this. The pilots automatically request that from the tower, says, I want this reroute via CPDLC. And the system is running at the FAA facilities. So the controllers already see this. And when they get that request, they also get an additional flag to it that says, it's been pre-approved via this tool. So you just have to accept, because essentially the tool also makes sure that that new trajectory is going to be conflict-free for the next 2 hours, because you don't want to send it over and then have to vector around other aircraft. So the controller will automatically accept it, click a box. It goes back to the pilot via CPDLC. They do an auto load into FMS, and they go off. And no phone calls. In the current method, you have to see the pilot has to call the dispatch. Dispatch has to pick up a phone, call the tower. Tower is too busy. They don't pick up phone calls. So therefore, these kinds of reroutes to the current methods don't really work. This is all done through automated trajectory negotiation with no phone calls. Just the limited flights that we have done, limited test, about 270 flights have participated. You see almost 200,000 pounds of fuel saved, and almost 500,000 pounds of CO2. along with about, which is equivalent to planting about 4,000 urban trees. We actually ran a previous experiment of this in Charlotte Airport, where the system was running with just one airline there, with American, for about a year period. And the objective of that one was simpler. It was, at what time should you push back from the gate to do a nonstop taxi to the runway, take off, and do a continuous climb to get inserted into an overhead stream slot without the weather component. So it was a simpler trajectory management tool. And that one, through that one just experiment, saved over 1 million gallons of fuel and about, times 5 of that in pounds of CO2. We had almost, several million pounds of CO2 savings. That was transferred to the FAA, and it's actually now beginning its national deployment, and it's already started national deployment at multiple airports in the United States. So as you can see, there's some serious reality behind the sustainability efforts. And we're also doing advanced air mobility. How do we integrate electrified vehicles into the national airspace? So for example, the main objectives there are, we want to do this in a scaled and safe operations. So what we're working on is development of the architecture and the functions and capabilities, integrated in-time aviation safety management systems for it, as well as the integration of autonomous vehicles. So that we can actually be able to use electrified systems en masse. And then last but not least is a focus on advanced capabilities for emergency response operations. How do we do automated flight management systems in what we call it ATM in a box, which is essentially a very portable, low power, mobile ATM system for management of firefighting vehicles and aerial assets. Because currently, through the manual ways, they only operate about 4 hours a day because it's an extremely demanding and dangerous job with limited visibility, limited capabilities. It's all manual. And we want to go to a 24/7 operation to enable firefighting. And that will help tremendously with climate change, because I just read the news articles about a couple of weeks ago where you look at the Canadian fires and the amount of CO2 produced there was, I think it exceeded US and Europe, combined output, I believe, if I was not mistaken. So this is essentially a huge need that we're focusing on as well. And of course, this is just a plan, and this is similar to perhaps what you'll see a lot of similarities where my colleague Andreas will speak in a moment, where we have essentially a set of timelines and specific objectives identified between now and 2050 on how to get to that Sky for All vision. So let me pause here and see if there are any questions.
Thank you, Akbar. Maybe we can switch on the light. Are there any questions? I think we have a few minutes left. While waiting for someone to raise his hand, I have a question for you, because you insisted a little bit about the fact that it's not for replacing human. It's really a support. Do you mean that it's one of the biggest barriers that you have to implement your new technology? Because I think we all agree that digitalization is the key. We will see it also with the next presentation. And in America, you have one single airspace. In Europe, we are fragmented, so at least we have some excuses. So could you maybe explain
Sure.
why it's so difficult to transition?
It's a great question. Like my portfolio, as you noticed, I'm responsible for aviation safety as well. So we do quite a bit of research there. And one of the big components of there that we work on aviation safety is what we call human contribution to safety. And when you look at humans and machines, there's a big difference. Human has I call 3 C's. The human has compassion, curiosity, and creativity. When you have a problem, you need those 3 C's. Automation will never have those 3. It will make a cold decision, and it does not have compassion. And also, should it run into a situation that is never seen before, it does not yet have the creativity. Yeah, the generative AI is beginning to sort of get there, but still, human creativity. I mean, look, we're researchers. You're all here for this last week. Why are you all here? It's due to your creativity, right? So those are the 3 C's that a human has that really helps the system. And the same thing, it has some I's, where the human is investigative, it's interrogative, and it wants to like look at something and says, what's going on here? And you're able to identify and detect a problem before it becomes an issue. Or, so those are the caveats that human has that we don't want to lose. So therefore, what we want to do is we want to have automation assist what the humans are really good at.
Thank you. Yes, I see a question there. The microphone is coming.
Nice presentation. My question is related to the wildland operations. When you're saying that you want to, quote unquote, gain the night, are you talking about introducing fully autonomous systems? Are you thinking about hybrid operations, crewed and uncrewed? Or are you talking about infusing sufficient technology to allow crewed operations during the night?
Okay. Great question, and those are the 3 sort of steps that you described are what we have in mind. So the ultimate objective is to do both daytime and nighttime heterogeneous combined operations of uncrewed and crewed. But that will take time. In the meantime, the globe is burning. So therefore, we're not going to wait for that. We're going to work it, but the immediate near-term focus that we have between now and 2030, over the next 6 years, is introduction of uncrewed and remotely piloted vehicles for nighttime operations to augment the daytime crewed. Because nighttime is segregated, so we don't have to worry about the mixing of the two. So it's a less complex problem that allows us to introduce a capability that doesn't exist yet. So we'll do that first. Then the second will be the combination of those 2 during daytime. And then the last step would be then the combination of those 2 during nighttime. So as you can see, it's sort of like a stepwise escalation.
Thank you. Any other question for Akbar?
And hopefully I did not misstate that, because we have our expert right there, Marcus, and he can throw something at me.
Okay, I have maybe another question for you, because you spoke about FFIs, and everyone is also, at least in the ATM world, about TBO. Mm-hmm. So what do we need to accelerate this? Because in terms of deployment, you are maybe not suffering from this lack of synchronization in terms of deployment in America. So what needs to be done to accelerate the transition to trajectory-based operation?
What needs to happen is 2 things. One is, I have my Lufthansa colleague there, and whenever we want to deploy TBO, it requires equipage. They need to deploy some box on the aircraft. Airlines are a very, the cost-benefit margin is very, very low. So the first questions the airlines always ask, what's the benefit? Why should I even equip? So the first things we need to do is do the kind of things that I talked about, where, for example, you saw that demonstration in Texas, where it shows the airline that if you're CPDLC and ADS-B equipped and you invest in that technology, you can get that service. So essentially, you paid back by fuel savings. So the first thing for us researchers is to do that equipage, the automation equipage benefits assessment and or technology development that helps the airlines offset the cost of equipping. The second one is communication, nav, and surveillance, because the current modes of exchanging data is not sufficient. As we talk about Sky for All, I have it up here on this chart, Sky for All will entail moving gigabytes and terabytes of data around the cloud. A lot of data being exchanged. And we can all agree, fans at 8 bits and 8 cars, just not going to do it. So we're going to need a different way of doing data exchange, ComNav, surveillance, and then there's a 4th letter, the S for security. So essentially CNSS. And those are the 2 main barriers, I would say.
Thank you. Any last question, maybe? Or I'm looking to the panelists because Lufthansa has been mentioned several times now.
Sorry,
You
I
are
didn't mean
fine
to
with
just pick
the
on you.
answer? That's fine. So, thank you, Akbar. It was quite interesting. A round of applause for him. And now I would like to introduce our next speaker. So we just heard the vision of NASA about the future of ATM. Now we are going to switch to the European side. So Andreas Boschen, our next speaker, is the Executive Director of the CESAR Joint Undertaking. And again, because the audience is not really air traffic management related, I would like just to explain very quickly what is the CESAR Joint Undertaking. So it's a European initiative aiming to accelerate the delivery of the European digital sky. So you see already some similarities with the presentation of Akbar. It's a public-private partnerships that coordinates research and innovation efforts to make the air traffic management performance better in terms of safety, efficiency, capacity, and environment. So now, Andreas, can you tell you more about how can Europe be more efficient and environmentally friendly sky to fly in the world? So, thank you, Andreas. The floor is yours.
Thank you. Good afternoon. Thanks for the introduction, Marilyn. You forgot to mention that Eurocontrol is one of our very strong members in this joint undertaking. It's an honor to address you here at ICAS, and it's also a pleasure to follow up on Akbar, because indeed he said many things I would like to say also, and it's good to see that our visions are very much aligned. So I think you will agree with me that our vision is quite ambitious, and I hope I can convince you in the next slides that we are on the right track there. Now, we are really seeing our mission to support net zero aviation, and this, Akbar mentioned it, it has been tackled as an objective at the ICAO level. We have also a European policy, the European Green Deal, and of course the industry is also, aviation industry is also looking into decarbonization. In Europe we have, for example, the Destination 2050 initiative, and all of this works nicely together. And when we are looking at the overall picture, how can we get there? You have seen this slide before. There are different technological pathways. New aircraft, Axel is sitting here, he will make it, the new aircraft coming, new SAF, sustainable aviation fuels, and so on and so forth. And we're having a bar which is called Air Traffic Management and Operations. And it is a very stable bar, which is not growing like SAF and the fleet renewal, but it is there. In the end, it will be 6%. But like Marilyn was underlining in the introduction, we have technologies which are ready now. And whatever we can gain in terms of sustainability, I think Lufthansa and other actors are interested in gain it now. So my message is we are making our contribution to the overall picture of decarbonizing aviation. So how is ADM doing in Europe right now? And I'm putting here some figures which are coming from Eurocontrol and which are publicly available. And it was not a very bad summer in public perception, but it was also not a very good summer if you look at arrival punctuality. So we are doing certainly worse than in 2019, which was the year before COVID. And you see also that the average delay caused by air traffic management, so what we call the ATFM delay, is up. And we have heard in other presentations here during the Congress, adverse weather, climate change calling. Adverse weather is making a big contribution now to this. And we have also issues in Europe with air traffic control capacity and staffing. And okay, CO2 emissions, they are a bit better if you compare to 2019, but we have also still to recognize the number of flights is still not there. What I would like to underline, and Akbar, you mentioned it already, safety. I think we have an excellent safety record in our industry, and we would like to keep it. And we have an average of 30,000 flights per day in Europe, and it's safe to take the plane. So in Europe, we are still highly fragmented, 39 air navigation service providers, 60 air traffic centers, and it's an industry, a sector where technologies take time to get operational, so it's a slow uptake. And if you look to the ideal benefit pool, so how much could we ideally obtain from ADM improvements in a gate-to-gate perspective, it could be 9%. 9% if weather is always perfect, if everything is perfect. But what I want to say, there is a chance to get this 5-6%, which we are supposed to bring to the overall addition of aviation decarbonization. So CESAR, joint undertaking. CESAR is an abbreviation. We love abbreviations in air traffic management. So CESAR stands for Single European Sky, Air Traffic Management Research. And indeed, Marilyn, you mentioned our job is to accelerate the delivery of an inclusive, resilient, sustainable digital European sky. We are a public-private partnership, more than 50 members. We are covering the whole innovation pipeline. So we have research institutions, but we have also a lot of operationals. Lufthansa is a member, airports are members, industry is a member, Eurocontrol is a member, and we have a bit of a budget. We're getting money from the European taxpayer, but we are also getting investments from the industry, and all over we have 1.6 billion for the next years to come. So our core tasks are to modernize air traffic management, and we do this with a strategic planning and monitoring tool, which we call the European Air Traffic Management Master Plan, and then we roll it out. We do research and development projects where we come to CESAR solutions, and then we don't stop there. I think it's very important also that research doesn't stop and leads to more research, but we manage to push research into operations, and therefore we are trying also to facilitate the market uptake by demonstrating, by coordinating, by supporting the delivery of CESAR solutions into the operations. So we have a digital European Sky program with 9 flagships, and I'm supposed to talk about sustainability. So obviously in the middle there is the aviation Green Deal. But if you look around, it's all connected. We need capacity on demand and dynamic airspace. Otherwise we will not become sustainable. We need virtualization. Otherwise we will not become sustainable. We need more in Europe. It's a very important topic, civil-military cooperation and interoperability. The airspace in Europe is definitely limited, and there are many legitimate users, and in particular the military, and civil and military have to manage together how we can ideally operate the airspace. Akbar, you gave a good example about space launches. How can we, let's say, minimize the impact on civil aviation, civil aviation, but I would say the same is true in Europe for military areas. Of course, I need to train, but how can we do this in a way that every airspace user finds its way? So you see, we are covering different aspects, and many of them are contributing to sustainability. Right now, we're having more than 70 projects in operation, which represent an overall investment of 600 million euro, and we have delivered the solutions. 136 are out, available on our website. Please have a look. And let me talk about them a bit. Like Akbar was saying, our solutions are bringing environmental benefits. And we are looking at a gate-to-gate efficiency, which starts with the idea of airspace design. I mentioned civil-military coordination, which goes into it, which goes then into flight planning and network operations, that the airplanes push off when it's the right time, and from the gate, that we manage this in an integrated way, and so on and so forth. And you can see here in this picture what is the potential of gaining kilograms of fuel and kilograms of CO2 if we are putting all this together, if we have a departure manager, if we're integrating the arrival and the departure manager, if we are getting on our way to TBO, Akbar replied to the question, if we have the extended projected profile, which allows the air traffic controller to better see the intentions of the airplane, and so on and so forth. Free route airspace is something which is implemented in Europe now in a cross cross-border perspective and which really brings some benefit. Maybe we had hoped to get even more, but it brings definitely some benefits that the airplanes can fly more unconstrained than before. So let me go a bit deeper in certain of our Green Deal solutions, just to show again to you research is coming to results and which are available and which we hope to see rolled out across the aviation community in airports, in airlines and in air navigation service providers more and more. So greener taxiing, this is very important, and there are different ways, taxibot, wheel tax, e-taxi and so on. And what is the best solution for a given situation? And there we are proposing to integrate AI into airport surface management, that the most appropriate taxiing technique for each flight can be identified and used. More sustainable approach and landing helped by satellite approach. You see the glide slope, you see the secondary aiming point. These are also things which bring benefits not only from a CO2 and fuel perspective, but also from a noise perspective. This still needs a bit of marketing, a market uptake, but from a research perspective, we have validated these solutions. And then oceanic flights, if we can also bring in satellite technology, that would allow us to have more data about the oceanic flights, and that would allow us to reduce separation buffers, and of course it would bring greater fuel efficiency. Then of course it is also time to look at the non-CO2 impact of aviation. This is a hot topic in Europe. You're reading it in the news, and we always try to bring in artificial intelligence to really have the right climate impact data, and then also to make the right choices, to develop the right solutions, how to mitigate, how do we reroute aircraft around climate sensitive areas without creating a negative environmental balance, so that the non-CO2 and the CO2 balance is the right ones. Seeing is believing. I spoke about free route airspace, so that planes can have an entry point and an exit point in a big airspace, and it is already in 55 out of 68 area control centers applied in Europe, and you see that we have also quite some important savings. Extended arrival management, so the planning for the airport starts 150 nautical miles, 200 nautical miles before, and we are reducing, if necessary, we are reducing the speed of the incoming flight, so to avoid the delay and avoid having the holding at the airport. And again, you see that this is not nothing in terms of CO2 savings per flight. So this is reality. This is not any longer research. But let's look a little bit in the vision. Let's look into Sky for All in Europe. We are updating the European Air Traffic Management Master Plan, and it is not our master plan. It's not the CESA Joint Undertaking Master Plan. It is really a roadmap on which all European stakeholders are working together. We have a vision. We have a way to roll it out. We have defined deployment priorities, we have defined development priorities, and we have calculated the benefits and the investment needs. So what you see on the picture is a draft, the proposal we sent out in July to our stakeholders, and we are confident that in December this year, this new Master Plan Edition 2024 will be adopted by the governing board, in which all the members of the joint undertaking are coming together. So the vision, the bold statement, making Europe the most efficient and environmentally friendly sky to fly in the world, how will it go? We see aviation and air traffic management integrated into an overall multimodal system. It is not only gate-to-gate from a passenger perspective, it is much more door-to-door, and also from a cargo perspective, it is to final destination. And this includes exchange with other modes of transport. This includes air taxis and other solutions to make a smooth passenger experience. And then we need to optimize each and every flight and to look at each and every climate impact of the flights, like I said, CO2 and non-CO2. And this will be possible thanks to technology, systematic, continuous, extremely precise optimization of all the flights that the aircraft can fly as best at its technical capabilities. And to get there, we need a new service delivery model, which is not the old current architecture of air traffic management with strong legacy systems, but with something which is more up-to-date, cloud-based, agile, where you have plug and play and these kind of things. And we need, of course, high connectivity, that the volumes of data which we need are flowing effectively and also secure in a cyber-secure way amongst the trusted users. And yes, we need more automation. The number of operations, of drone operations, of air taxi operations will simply too much to be handled by the human. So we need more automation to handle also the non-nominal situation. And this means we are looking at a new way of the human working together with the machines. The human-machine teaming is very important. And we will come to a situation where the human can trust the system and will intervene in the most complex tasks and leave many things to automation. So, timelines. We are doing things, we are deploying things right now, but the next 3 milestones we are looking at is doing research in the next 5 years to complete our vision of the digital European sky, 2030. In the next 10 years to deploy what we have, which will make already a big change and will improve air traffic management in Europe quite a while. And then by 2045, we would really like to see the digital European sky becoming reality across Europe. And in order to do so, we have defined 10 strategic deployment objectives, which are based on research solutions available. And they are covering all kinds of things. You see number 10 is about innovative air mobility, drone operations, and so on. But from a sustainability perspective, I would like to highlight the number 2. We would like to optimize airport and terminal maneuvering area, or TRACON or TMA environmental footprint. Other areas are also important for the environment. Number 3, dynamic airspace configuration. Number 5, Akbar replied to the question on TBO. We are absolutely aligned. There are things to deploy now, and there we need a bit more research. And this is then also number 7, the air-ground connectivity, the multi-link. How can we exchange more data, ground to air, ground to ground? So for all of this, behind all of this, there's a lot of material about technical solutions, standardization, regulatory frames, how to get there. And this is what we want to do, what the stakeholders want to do in Europe over the next 10 years. And then looking into the research area and the development priorities we are having defined together. On the right side, you see the early part of the innovation pipeline, exploratory research, where again we are looking into climate impact, but we are also looking to future technologies. What will quantum sensing and computing, can it bring anything to air traffic management? I think it's time to start looking into it. In a bit further down the innovation pipeline, applied research, we are looking into what we call in Europe Airspace, so that's the integration of drones and air taxis into the airspace. And Axel, you will like it. We will also try to see what air traffic management, what airspace has to do to integrate the zero and low emission aviation, which is coming hopefully as from 2035. On the more mature side of industrial research, you see again the things which need to be done on trajectory-based operations, on the connectivity, the multi-link between air and ground. And then the next 3 ones, which I would like to stress, are really the new service delivery model, the new platforms which allow for human-machine teaming, which allow to become agile, to be scalable not in hours, but in minutes, and this is really important. We will put a lot of efforts on these research priorities over the next years. If you are interested, somewhere in 2025, in the first quarter, we will publish calls for proposals, which we will put a lot of our money into to roll out these 12 strategic development priorities. So, there's no free lunch, also not in air traffic management. It needs investments, yes. So we have made our calculations. It's a bit, of course, crystal ball. How will the world look like in 2050? But still, according to our knowledge now, according to the assumptions of the experts, I would say the investment needed, cumulative, that's the right English word, cumulative, over the 25 years, it is not so much. It is 25 billion euros as we are calculating it. And if you put then the benefits into it, they are simply overwhelming. So I think we have a very, very good case. Some people in Europe might have read the Mario Draghi report, which came out this week about innovation, about competitiveness in Europe. Well, he was saying Europe needs 100 billion euros per year to decarbonize aviation. Well, if I could get 25 billion for 25 years, I'm already fine with it. And it is not only about monetary benefits. I mean, there are real benefits in terms of safety, in terms of efficiency, in terms of capacity, and in terms of environment behind. And we have made a calculation for the CO2 so we could save 400 million tons of CO2 with this trajectory, and that is again then the 5 to 6% I was stressing at the beginning of my presentation. So we think we are really there. There is a chance to make Europe the most efficient and environmentally friendly sky to fly in the world. It will not be an easy task. It will be hard work. We have to do it together. We need all the stakeholders in the innovation pipeline, from the research to the industry to the end users, to work together and not next to each other. But what is the alternative? Can we afford not to modernize air traffic management? Can we put it aside? So our strong conviction is no, air traffic management has to do its part to decarbonize aviation, to keep aviation safe and efficient. And voila, that is maybe the last word from my talk. Thank you very much for your interest.
Thank you, Andrea. Can we switch on the light? I see already a hand raise. Yes.
Fred Abbink from the Netherlands. Thank you very much for your very interesting and very optimistic presentation. Single European Sky started 20 years ago. And we say if we really in Europe want a single European sky, we need better cooperation between the ANSPs and their bosses, the governments. Can you say a little bit what's your expectation that we will reach this single European sky using the technology integrated, provided by CESAR?
Thank you very much. As a matter of fact, in 2004, I was in the Single European Sky unit of the European Commission. I worked on the first implementation of the first legislations which were done in Europe, so I have also a personal view on the question. We are part of the Single European Sky. We are definitely the technological pillar. We push it from the technological side. I'm not a politician. I'm not a minister of transport. I'm not a member of the European Parliament. So we leave this. I'm not discussing politics here. But I think we have a chance via innovation and digitalization to make it a better European sky. And as a matter of fact, I would also like to stress, when we were preparing this master plan, we saw a lot of interest by the air navigation service providers. The big 6, 7, 8, 9, 10 in Europe have made a declaration in July together with the industry, the ground industry, that they want to work on it. They want to get to this new service delivery model. So I have to take their words and ask them now to deliver. And that is a bit our challenge. I'm optimistic by nature and by job description. And again, let me be as political as that. What we haven't achieved politically over the last 10, 20 years, maybe it is time to do it now via digitalization and innovation. So I think, and I hope this is also my message to whoever becomes the next Transport Commissioner of the European Union.
Thank you. Maybe I can just add to it. How can we find incentives for the ANSPs to work more closely together? I know we have 1944 ICAO, and every country is responsible for its infrastructure, its air traffic controls and systems. How can we make this step that we say we integrate ANSPs? FABEC, the Functional Aspect Block, was maybe a first step to that direction. We have to find ways where we can convince our air traffic controllers and their bosses that cooperation is necessary for the future for Europe.
I'm looking at my moderator because she wanted to say something also, so maybe...
Yeah, but it was related to your first question, and it will be also related to your second question now. And I will speak more like Eurocontrol because I'm also representing the network manager here. Let's be clear, it's not because the political single European sky is not implemented that it means that the ATM community is not working. Huh? So let's be clear, a lot of improvement has been done. The problem now is to see, and what happened during the summer, it has been mentioned by Andreas, but the delays are increasing. So we are at a point at which, if we continue to work as we are working today, we will not make it. As simple as that. So it's why we need to go to this new technology. So by default, the ATM community in Europe will have to follow. We have just a presentation from NASA that also confirmed that we are in the right direction because we need more digitalization, we need more automation, because the complexity is increasing. During the summer, we see extreme weather conditions that are increasing as well. It means that the complexity of the network is increasing as well. We need more predictability, and to have this predictability to be able to manage the network, we need the proper tools to do that. And it's why I think this ATM Master Plan update is really tackling this. It was so challenging to find a kind of consensus because, of course, every stakeholder have its own agenda and also their own constraint. But I think now that we are at a point at which at least we all agree we need to change. So it will be my kind of answer to your two questions.
And we try to make the different pillars of the single European sky work together. So if I speak about investments, the ANSPs need to make the money. They have to get the money for these investments. So we need that the performance scheme is supporting innovation and that ANSPs do not get punished for investing into innovation. So that is a discussion we are having. We have now I'm in jargon, RP4, which is now the next performance period where we are already trying to do this. And I can tell you for the future, we have to have a performance scheme which is supporting even more innovation as it's now doing. So there are also, I think also we should be optimistic here again.
I see another hand just behind you.
Hello, my name is Marcus Johnson from NASA. Thank you for the great presentation. I had just a question. Is you're looking at trying to hit that 6% reduction in carbon emissions, but you also mentioned that kind of some of your current delays were due to weather. As we're trying to kind of seek efficiency, kind of the climate is impacting the world around us, and we're going to start getting more and more weather and challenges with disruptions to air traffic. How do you view incorporating more resiliency within your plan and within the technology such that the gains that you're making in efficiency aren't canceled by the disruption due to climate change?
Right. I mean, great question, and I think in the sessions I attended this morning, there were some projects tackling it, how to integrate weather better into the ADM system, and how to use then also machine learning, artificial intelligence to better forecast. So I think we have to research, and it's good to see that there are projects. There was an American project in NAF Canada, and I think MIT Lincoln Lab was one, and there was a European today. So I would say let's let these projects continue and let's operationalize them, because I think at both sides we were saying at the end we need to bring it to operations now. So I would reply, great job by the researchers done already, and to be continued, and to introduce it. I guess Lufthansa would not mind getting better weather forecasts and then have a better avoiding these adverse weather conditions.
I will complement your answer from an operational point of view. So this is a matter that we are taking very seriously. So we are managing it also from directly in the operational room by increasing collaboration with all our stakeholders to try to look at the networked effect, because this is also the problem. When you have a problem at one specific area in Europe, it will impact the whole network. So we are trying with all our stakeholders to find solutions to better manage the network effect. Now, in terms of research, we are of course working with Andreas, with Cesar, and we have also different working groups working on climate change adaptation and resilience. And there are two kinds of working groups. The first one, it's more about what could we do to mitigate the effects. So we are discussing with the airports, for instance, to prepare, their infrastructure to be better resilient, or to maybe do some investment that could be done short terms, like installing some pump around the runway. But we have to go further beyond the aviation sector. I'm going to give you an example. In Greece, they were fully prepared for de-icing and blah, 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 because it's not used, that you have snow in Greece. But the public transport were completely out, And then the air traffic controllers were not able to reach the airport. So the plane was there, the runway was ready, but there were no air traffic controller in the tower. So this is the kind of things that we need to work. So we are also working with the beyond the aviation sector to try to tackle this. And then there is also the scientific research about better measuring the impact of climate change on aviation. So we are working on all the different aspects, but this is clearly something that we are taking seriously. We started to work on this several years ago, and as Eurocontrol, we have published different reports on this matter, by the way.
You see, they are a very strong member of my organization. They're really great.
Yes, another hand raised.
Of the many additional aspects associated to an initiative like this, for example, legal and regulatory aspects or public acceptance, I would like to focus on one particular aspect, which is training necessary to make this a reality. How much of a challenge do you think this is going to be, and what specific measures are you taking towards this? Thank you.
I would maybe even broaden it as the acceptance by the operationals of all changes, of all innovation. I mean, we try to involve the professional staff organizations, the pilots, the ETCOs, the ATSEPs as much as possible. We're working with these organizations, IFATCA, IFACEA, ECA, whatever it is. And we try to bring them into our projects also, that at project level, at research level, the operationals are present, can feedback, can say, this would help me in my daily work, or this would not help me. So we try to have this loop, and so we have a dialogue with them. Obviously, you're talking to specialists who are in their job for many, many years, who are very good, who are excellent, who are dealing with safety issues on a real time. So they're taking it very serious. So it's convincing the people and showing them that technology can help them. So I want to stress again, I'm not afraid of anybody's job. Automation doesn't mean we will lay off engineers or whatever. To the contrary, I think in Europe we are rather lacking a skilled workforce, and it is rather in our interest to go for automation. So we need the humans, but we would also be clear, jobs will evolve. The job profile will evolve, but also into something which is maybe even more interesting and more rewarding also than what currently, let's call it, routine jobs are. And I hope we are able to take the people with us. That is a bit what we try. I cannot force anybody to go for innovation. I have to convince. We have to convince that our solutions are as good for them, that they make a difference for them in their daily job. And I'm proud to say many of them are, and we are speaking to controllers, they say, what I saw in the trials is very good. I hope I see it rather soon in my organization. Then we are at the question how to accelerate market uptake, how to bring research results which they like in the lab rather quickly into their daily operations. That's a good challenge. So let's take the people with us.
Any other last question? I have maybe a provocative one, but it will be for the two of you actually, because it's because you said that the future it's digitalization, cloud-based solution, but we are in an era in which we have cyber attacks which are increasing. So it could be very surprising, specifically because you mentioned safety, that despite these cyber attacks that are increasing, we still want to continue to go into that direction. So maybe could you highlight me how we are going to deal with that and why we want to pursue in that direction, seeing the ongoing context?
Thank you. And I think there was a question I was asked earlier from the audience too, and I think I mentioned that was the CNSS, the fourth letter being for security. We absolutely are focused on research there because we have to do security in a different way because, you know, trying to do automation without data, just not possible. The two go hand in hand. And in order to improve efficiency and allow the user, give the most power to the end user to make the decision, that's why we have to go to a cloud interface, because we're trying to move in the action to the end user. Remember once upon a time, I mean, phones, well, not remember because I hope nobody remembers it, but once upon a time on the phones, you had to call a switchboard. You would pick up a phone and you dial into a switchboard, you say, I want to talk to so-and-so, and then they would do the manual switching to connect you, right? We will go now, we're our own switchboards now, right? It's efficiency. It allows you to connect quickly. So that's what I mean, taking the decision to the user. So as we do that, there is a major research challenge, and this is where we're doing research. You need to make sure that the data, what data needs to be where, for what reason, and how much of it, and how late can it be, right? And can you make sure that that data has not been adulterated, it's not been changed from the source to the destination? Or for that matter, even if the data is not adulterated, the recipient of the data, it does not get different information. So for example, you could say that could be an aircraft. One doesn't even have to spoof your GPS. But if you can, instead of you're squawking your own GPS, you know your location, but if the ATCO is getting a signal that says, no, this is his location, they're going to make decisions on false data, right? So this is another kind of adulteration. This absolutely is a major research area to make sure that that we address all of these things.
If I can just add, I fully agree. There are many network industries or sectors which are affected by cybersecurity. And when you look at finance, look at medicine, look at energy, so it's a common challenge. And I think we are also, particularly in Europe, we are also trying to tackle it together. So let's also look what solutions are available in areas of cybersecurity by other sectors, and let's look whether we can apply them to aviation. And I think in many cases we can. But again, it needs research, it needs adaptation and so on. It's something, the new system we will build up has to be cyber secure. Absolutely.
Yeah. Thank you, Andreas. Thank you. Big round of applause. And now I would like to introduce the next presentation. So it will be a joint presentation between DLR and NASA. So for your information, DLR and NASA have a strong long decades collaboration working on better assessing the impact of aviation on climate change and also working on contrails. So it will be a quite interesting presentation. So I would like to introduce our speakers first. So first it will be Dr. Richard Moore, who is research scientist at NASA's Langley Research Center. He's the principal investigator for the recent NASA Aeronautics-funded Boeing Eco Demonstrator emissions flight. It's difficult to say for me. And deputy project scientist for the ND Max Eclipse 2 control studies. And he will be joined by Dr. Christian Voigt. She is the head of Department of Cloud Physics at the German Aerospace Center, DLR, and professor for atmospheric physics at the University Mainz. She's the principal investigator for multiple recent airborne studies, including the recent Eclipse 1-3 and Vulcan flight experiments studying contrails and aircraft exhaust. So both of them will discuss about the last findings on how SAF, so sustainable aviation fuel, and advanced engine technology can reduce the climate impact of aviation, but from an operational point of view. So please, come on, I give you the floor.
Thank you very much for that kind introduction and the invitation to speak in what has been a really outstanding track. And so I live about 3 hours south of Washington, D.C. in the U.S. under one of the major skyways of the United States. And when I'm coming in the mornings, it's not uncommon to see these line-shaped clouds crisscrossing the sky. And a few hours later, I'll emerge, stretch my legs, and get some lunch. And those line-shaped clouds have spread and sheared into continuous wispy cloud decks of cirrus clouds. And so we know that those clouds interact with the incoming sunlight, reflecting it back to space and having a cooling effect. And they also serve as a heat-trapping blanket for outgoing radiation from the Earth. And so balancing those two competing effects, as well as asking the interesting thought question, if that airplane had not flown through the sky in that time, would that cloud have formed anyway? These are great questions that we really need models to uncover. And so we have some models that are able to do the global bookkeeping, and those models tell us that the impact of contrail cirrus clouds on our climate today is on par in magnitude with the cumulative emissions of aviation CO2 over the last century. And so this is an important topic, and I want to emphasize that this isn't to say that CO2 isn't important. We know that is, of course, paramount, and we've heard that throughout this week. But we have to worry about non-CO2 and particularly contrail cirrus clouds as well. Luckily, we think we have a menu of different options over the short, medium, and long term that we may be able to use to address this. And in particular, we're looking at advanced engine combustion technologies like lean burn and geared turbofan that can reduce the soot particles coming out of these engines. We can also look to alternative fuels, hopefully sustainably produced, that may be lower sooting. And then over the medium term, we've heard some about, and the tools that were discussed in the previous talks about air traffic management, applying that to aircraft at cruise altitudes to potentially avoid regions where we would form a contrail in the first place. And so thinking about the effects of engines and fuels, NASA, DLR, our industry colleagues and academic partners have been working in this area for multiple decades, at trying to understand how changes in fuel chemistry affect emissions coming out of the tailpipe of engines. And so our focus has shifted over the years. In the 90s, there was an emphasis on looking at fuel sulfur and seeing if there was a need to desulfurize jet fuel. And then in the 2000s, we started thinking about alternative fuels, not sustainable fuels, but alternative fuels. So low aromatic, low sulfur fuels, some of which were produced very unsustainably via the Fischer-Tropsch process from, say, coal or natural gas. But those fuels gave us our first indications of what the effect of those different chemical formulations would be on emissions. And also the community came together through SAE and other organizations to figure out how to measure this in an intelligent way. As we got good at that and started to get our feet wet on the ground, meanwhile, the ASTM certification process was playing out, and in the 2010s, we were able to do our first set of flight series with the recently approved 50% blends. And now in the 2020s, we're working with the Boeing Eco Demonstrator Program and the Airbus Vulcan project in order to explore not only the blends, but the pure 100% sustainable aviation fuels. And we're looking not just at aircraft of opportunity, but the modern combustors representative of the fleet. And so what have we learned? And so let's jump into some data to make this case. And so I'm showing here some of the data that we collected in collaboration with the Boeing Eco Demonstrator Program. This was a ground test that we conducted back in 2021, where we sampled the exhaust from one of their really clean LEAP 1B engines on the 737 MAX. And so I'm showing two graphs here. The left graph is the NOx emission index, grams of NOx emitted per kilogram of fuel. And it's plotted versus our thrust metric. So in this case, we're using an engine fan speed. So the left-hand side of the graph is representative of idle. The right-hand side of the graph is representative of a takeoff thrust. And on the right is our carbon monoxide, which is a tracer for incomplete combustion. And we looked at 4 different fuels. We can do that on the ground. We can be a little bit more flexible with the fuels that we're putting into the aircraft. Of course, our baseline is 100% Jet A fuel, and we looked at 100% sustainable aviation fuel. This was a hydrotreated esters and fatty acids fuel, HEFA. And so except for a trace amount of contamination, it really has 0 aromatics and 0 sulfur. But of course, that's not a drop-in fuel that's available for use today. And so we also looked at a 50% blend of SAF and a 30% blend that would be more representative of what you could actually utilize now. And that gives us a good indication of when we talk about 100% drop-in SAF, we're looking at fuel chemistries very similar to what we're calling here the 50% SAF blend. But what you see on these graphs is that as we vary the fuel, we're not seeing very much change in the emissions of these trace gases, and that's expected. These are driven by the temperature in the combustor, the efficiency of the combustion. But if we look at the particle emissions, it tells a very different story. And so the graph on the left is our non-volatile particle number emissions. So this is the number of soot particles emitted per kilogram of fuel burn on the same thrust N1 x-axis. And if we just focus on the variation in the fuel, we see that white line starts out at idle with a typically high soot particle emission index, very similar to what we see for legacy engine technologies like the CFM56 engines that we've tested for many years. And what's unique about the LEAP engines is as we move up in thrust, the engine stages and enters a lean burn combustion mode. And we see that the soot particle emission index drops by 3 orders of magnitude, down to some of the lowest values we've ever measured. When we look at our blends and our 100% non-drop-in sustainable aviation fuel, given by the green line, we see benefits across the board. And so we're seeing orders of magnitude benefit associated with the non-drop-in SAF at idle when the engine isn't staged. And we're seeing an additional benefit on top of what we get already from the engine at those high thrusts. The graph on the right shows the total particle number. So this includes those volatile particles that are also co-emitted with the soot. Things like sulfuric acid that maybe comes from the fuel sulfur, unburned hydrocarbons, and also lubrication oil that may be vaporized and vented outboard of the engine. And what's interesting to see here is that for the low aromatic, low sulfur fuel, the non-drop-in SAF, we see actually a benefit associated with the staged combustion. At high thrust, we're seeing decreases in the volatile particles. But when we're looking at our Jet A fuel, which has a nominal sulfur content on the order of several hundred ppm of sulfur, we don't see that effect. And so we're emitting high sulfur concentrations across the board. I really love ground data. I think it tells us the context of the way that the engine is behaving across the full range of operation. But of course, when we're talking about contrails and the effects of emissions at cruise, the ground data we know is just not representative of the low temperatures and low pressures that the aircraft experience in flight. And so we've done a number of flight tests over the years, often in collaboration with our colleagues at DLR and other organizations, to look at the effects of the blends at cruise. And those experiments in the 2013, 14, 2018 used our aircraft. We were using NASA's DC-8 aircraft as the fuel burner, or the DLR Atra. So older engine technologies, but giving us a sense of what blended SAF may do for cruise emissions. And as I mentioned, now here in the 2020s, we're working with industry, Airbus and Boeing, in order to look at the best engine technology on the market using the 100% SAF. And so I'll give you an example of what this type of experiment looks like using last year's Eco Demonstrator Explorer program collaboration between NASA and Boeing and DLR. You can see NASA's DC-8 flying laboratory here taxiing out at Payne Field near Seattle, Washington. And our fuel burner in this case is a pre-delivery 737-10. And the 737-10 has those LEAP 1B engines that we tested on the ground. And it's flying two different fuels, the 100% non-drop-in sustainable aviation fuel, and also a specially procured low-sulfur Jet A fuel that we were using as a reference. And you can see the DC-8 taking off afterwards, which Christiana and I were on, along with our science colleagues. And you can see all of the different probes and inlets sticking off the top of the airplane, as well as the windows. We're able to draw air in from outside and send it to a suite of chemical and physical instruments that are able to measure the particle properties, the trace gas properties, and then also some exterior mounted wing probes and fuselage mounted probes to measure the contrail ice crystals. And so the pilots would join up. Here's a view of the interior of the DC-8, so you can see the scientists up walking around, consulting with each other about the data that's being collected in real time. And the DC-8 is a headset environment, so we're able to talk over the noise of the aircraft and all of the different instruments. And it's a lively environment where we're able to say in real time basically how well the pilots are doing in putting the aircraft, putting those inlets into the contrail where we're seeing signals and where we're not. We also have plenty of real estate to test novel sensors. And so we flew for the first time some small water vapor sensors that Boeing is testing and developing and that are being developed through NASA's SBIR program in order to improve our ability to measure ice supersaturated regions at cruise. And so we were able to bring those sensors on as piggybacks to test alongside our state-of-the-art research-grade instruments. So this is the typical view from the 45-degree camera. The plane would start out above the contrail, and the pilots would descend into the contrail that you can see here. And the goal was to try to stay out of those primary wake vortices that might roll the plane or make us wind up upside down, and sample what we call the secondary wake, which is that ice that you see detrained at the top of the contrail. In addition to that, I'm getting ahead of myself. And so we were able to put the aircraft into the plume, and the pilots were very good at bringing it in and sustaining the measurement and then bringing it out. So we were able to get a background and then an in-plume and then a background sample. And so this is showing an example time series of some of the measurements we were making. So the top trace is our carbon dioxide mixing ratio. That's our fuel transfer function. The purple trace is our contrail ice number. The blue trace is the total particle number, so reflecting the contribution of those volatile particles. And the red trace is our soot particles, our non-volatiles. And you can see distinct periods where we see elevated CO2, ice, total particle number associated with when we're in the plume, and then it drops back down to zero or near background when we're out of the plume. And while we see enhancements in the CO2 and the ice associated with the contrails and those total particles, it's really hard to discern any soot coming from these engines. And that's characteristic of those 3 orders of magnitude reductions that we see on the ground. But what we're also seeing is that the reduction in soot doesn't translate directly into proportional reductions in ice. And so we're starting to wonder, well, what is then nucleating those ice crystals in the contrails? And the obvious culprit is the other particles that are being co-emitted. In addition to the in situ sampling, we also had an advanced high spectral resolution LiDAR on the aircraft. So we were able to fly a couple thousand feet above the contrail and profile it, sending a laser beam pulse down and measuring the light that gets scattered back up. And so you can see an example backscatter image on the left here. The y-axis is the vertical distance in feet, And the horizontal cross-section is actually time as the aircraft moves from the left side of the plume to the right, and we're able to profile and see the structure of those rotating vortices and the secondary wake. So at this time, I'll hand it over to my colleague, Dr. Voigt, to continue the presentation.
Thank you. Thank you for this excellent introduction and first part of the talk with first results from ground and some from flight measurements. I will expand on this and show more results from the flight measurements from the recent campaigns. And I will start here again, going back to the Ridge-Clench-Lean engines and the A350 measurements, which we made together with Airbus, or led by Airbus, and together with Rolls-Royce, where we tried to measure the effects of 100% SAF on particle emissions and on contrails. In addition to other emissions, we know that SAF does reduce the CO2 footprint if it's produced sustainable with renewable energies. But we also learned from those experiments in flight, but also on the ground, that there's a potential to also reduce the particle emissions and the contrails, which also contribute, as we heard about, half to the climate impact from aviation. So non-CO2 is about half the order of magnitude as a CO2 climate effect from aviation. But those contrails have short lifetimes, so this effect can be reduced fast. And that is something which we have to keep in mind when we consider our climate, because the fast reductions are really needed to achieve our climate goals. So here we probed with our small Falcon aircraft. You see it here, the emissions of the large A350 aircraft. Actually, the size of the Falcon fuselage is smaller than the size of the engines of the A350 aircraft. So it's really impressive when we go in and fly there. And the A350 had these Rolls-Royce Trent XWB engines burning 100% sustainable aviation fuel from Neste. And I think you saw some results and some photos also in previous presentations. And in expanding a bit more on the soot to ice or the contrail effect, I will want to explain a bit what we measured, and I have to go back to theory here. What you see here is the number of soot particles that are emitted per kilogram of fuel burn versus the number of ice crystals which are formed in contrails, again, versus kilogram of fuel burned. And for the current engine techniques, Ridge-Clench-Lean engine techniques, we are in the soot-rich regime. So we start in the upper end here, and there we see that about every soot particle here, 10 to the 16 soot particles, form an ice crystal. So that's the soot-to-ice correlation. So now there's the question, what happens with the newer engine technologies or with the 100% sustainable aviation fuels? Do we walk down that curve? Because the number of ice crystals is related to the climate impact from the contrails. So by reducing the number of ice crystals, we can strongly reduce the climate impact of those contrails. You see that this curve is kind of decreasing, this one-to-one line. It doesn't go to this lower end here. It's increasing here again. And that's the theory which predicts that volatile particles, sulfur, coming from the sulfur from the fuel, also could lead to ice activation. All this is at cold temperatures, at 10 degrees below the formation threshold for contrails. At warmer temperatures, this lower line here is happening eventually, or that's what the theory says. So not every soot particles, but eventually every 10th soot particles forms an ice crystal. So less ice crystals, less climate effect. And also that doesn't go down in a one-to-one line, because here we have immixing of ambient air, which could also lead to activation of ice crystals. So that's what the theory tells us, but let's see what happens really in flight in those conditions. And I will start with the results from the ECLIF 1 and 2 missions, which we performed together with NASA, FAA, and many colleagues on this 50% and 30% SAF blends. These are those upper points here. And we just compare similar contrail conditions. So all at very cold temperatures, 10 degrees below the Schmidt-Appelmann, and at relative humidities between 105 and 110% to make those data comparable, because we measure a large variability of emission indices in contrails due to natural conditions. So this is for similar conditions. The upper
black square here is a Jet A1. And here we have the reduction of the 50 to 30% blends with different composition. We see a reduction in soot particles and in ice crystals and a reduction in the climate impact. So that was for older engine technologies, V25, 27 aircraft. But now we performed the Eclipse 3 mission together with Airbus and Rolls-Royce with this newer engine. And you see that for the Jet A1, we already have a large reduction. It's an order of magnitude in particle emissions. So the new engine configuration really help to, they provide strong benefits for climate. And then we again have a reduction for the 100% SAF, which adds to this reduction. So that is what we explored for the rich quench lean, the current engine technologies. But of course, it's a question, what happens here in this low soot regime? And there's an extremely large span of predictions from the model. So we wouldn't know, would we be here in the lower range or in the upper range? And that's why we performed those additional measurements in the Boeing Echo D mission, and I will show some results later, but I will start now with the Neofuels Volcan project led by Airbus, and where the Falcon was chasing an A321neo with the LEAP-1A engines. And I will also show a slide film on these emission measurements, which is also very impressive also when you're sitting in the aircraft. It's really rather turbulent when you get into the plume. It's very shaky, and it's like going on a gravel road with very, very high speed. With a small Falcon, we were able to penetrate the plume in 50-meter distance to the preceding aircraft, because the Falcon, due to the size of the Falcon, it wouldn't go into the wake vortices. So that's the advantage here. And you see how we were chasing measuring contrails. And here we are going to such a near field sequence, where we really almost hit the preceding aircraft. I think it's at around 30-meter distance at both aircraft flying at high speed. We get in and out of the plume and then measure the emissions, the trace gases, the particles, and then we get a good contrast also to the background atmosphere, which we are also measuring. So also the pilots are very experienced, they are trained in order to do these maneuvers safe together with industry, working together, and also that's the reason why we really enjoy working here with industry in order to get results which you cannot get when each partner is working alone. So what are the results here? You saw some timelines from Rich Moore before. Again, we have the particle number emissions, then the trace gases, the static temperature and pressure versus the flight time here. And what you see here on the upper line, each time we get into the plume, we have enhanced particle concentration, enhanced trace gases, enhanced temperatures, and we perform a sequence of measurements, 5 measurements at same engine conditions, and then change the engine conditions or change the fuel. That has been done by Airbus and this is a cooperation also with the French partner Safran, Honora, Dassault, who are operating the aircraft. And what you also see is similar to Rich Moore's plot, so that's the rich burn condition. So we have non-volatile particles, which are the dark gray trace, and volatile particles, so liquid particles, which are this lighter bluish trace, enhanced when we get into the plume and back to background conditions here. And what now happens in this lean burn condition, when this lean burn condition is switched off, you see that there's almost no soot particles, similar to what Rich showed in flight and also on the ground, but we still have these volatile particles which are emitted. So you clearly can indicate the lean burn conditions. This is forced rich burn, but in the lean burn, there's almost no soot. Here we changed our dilution system. That's why we got some particle measurements here, but the order of magnitude reduction, this is all logarithmic scale, is large. But now to be more quantitative. So what does this really mean in terms of emission index? And that is shown here for the A321neo. Again, we have the forced rich burn regime. So Airbus was able to really trim the engine in order to get comparable conditions in rich burn and in lean burn. And the light gray, that's the non-volatile particles here. In the rich burn regime, we have 10 to the 15 non-volatile particles emitted, which then lead to contrail formation. In the lean burn, we have this strong 3 orders of magnitude decrease in particle emissions, while we still have those volatile particles. The total particles are rather high. So, of course, it's a question what now happens to the contrails. Do they form in similar low numbers or not? So we can go back again in this Kercher plot. And now I do not show comparable conditions, but all conditions measured. And that's why we have this variety of points here, just to see the range where we measured emission indices. That's again the forced rich burn regime, similar to the rich quench lean techniques. And now in the lean burn regime, we have this again 3 orders of magnitude reduction while still having similar number concentration of ice crystals. So it seems that something else gets activated. We know that there's no soot particles, so something else gets activated. It could be volatile particles, it could be ions, could also eventually be oil from the engine oil. And that's now the next question. So what is the source of those particles, of those contrail ice crystals which form in similar numbers as in this rich burn regime? So the measurements here were performed with a Jet A1 and also with a HEFA aircraft together with Airbus. For ECO-D, there was a special care to also use a desulfurized Jet A1, and also that is a pre-delivery aircraft with a brand new engine. So it's really a very, the best configuration, the cleanest engine aircraft configuration we could get. And that also then helped to reduce the ice crystal numbers quite a bit. Again, this is an order of magnitude. This is all logarithmic scale. So we got to cleaner conditions here, but still not reaching the background conditions. So now we have to switch gears a bit, or ideas a bit. Before we thought, well, we know the aromatic content. Aromatics are good soot precursors, so each aromatics lead to soot, and each soot particle forms an ice crystal, and we can understand the number of ice crystals and the contrail climate impact arising from them. But now we learn that at the low soot regime, it's other particles that do form the ice, and therefore we have to switch our thinking, and we have to consider now the total particles, that is the non-volatile and the volatile particles, which are indicated here again versus ice crystal number. And then you see that this falls nicely within this. This is a 1-to-1 line now. This is a 0.1-to-1 line. So we can kind of predict the ice crystal numbers when considering not only the soot, but also the volatile particle emissions. And that is something that has to be monitored in future, measured in future, to also include the volatiles, which might have been formed by ions, by this engine oil, but also by the sulfur content of the fuel. So it might also help to reduce the sulfur content of the fuel, as we have seen in ECO-D. And that is also shown, I think, in the next here. You have the ECO-D results again, less volatile particles due to the low sulfur content and to the very, very new engine. So what is the minimum in climate impact from aviation? What we expect there with this new theory. So also it helps. We don't have to care about this very clean condition. So we think that probably we expect a minimum in the radiative forcing of contrails for engine emissions in the range of 10 to the 14, 10 to the 13. And that will be also the goal of the new experimental campaign, to really investigate, do we find a minimum in contrail ice crystal numbers, which then relate to a minimum in the climate impact from contrails. So as a conclusions, we have performed together with the partners, with NASA and with industry, multi-decade international collaborative research efforts to quantify the effects of SAF on engine soot particle emissions, but also on contrails and on climate. And really this work can only be done in a collaboration. We are very happy to collaborate with industry because the results can enter industry in a very direct way. We don't have to wait for publications to come, and industry can design the engines and the fuels in a way to really reduce particles and reduce the total climate impact from aviation. We have learned that the stage lean burn engines and the 100% HEFA yield strong particle emissions, in addition to lowering the CO2 footprint for the 100% HEFA. and the 100% HEFA also lowers the particle emissions in the at the low power conditions, so near the apron on the ground, which also helps for airport air quality then. And as we reduce soot, there's an emergent need to measure, to quantify, and to characterize, and eventually also to decide on to reduce those volatile particles. And that's what we want to do in probing. As we have seen, there is theory, but we need really the in-flight experiments to probe and to test the theory. So in 25, we'll have together with NASA and Pratt & Whitney, also with Airbus, some ground and flight tests in order to get this to this minimum contrail point in this case. And also at DLR, we have a new aircraft, the Uplift, the DO 328 aircraft, which is shown here, which is just integrated. So we started integrating our instrument in our Falcon again to probe the emission of this turboprop aircraft, which is comparable to the small and medium range fleet. And for that, no engine emission database exists. So we really have to probe the emissions in flight, the reference emissions. Also, that aircraft can go to 10 kilometers altitude, so we can measure the contrails. We'll make measurements with Jet A-on and with the P2L fuel in order to build a reference for future hydrogen technologies, which are the only technologies that do not emit any CO2.
Thank you. Thank you, Christian. Thank you, Richard. And I thought that SAF was an easy one, you know, but apparently it's clearly not so easy when it comes to emission reduction. We are a little bit late, so I'm not sure we have time for questions, unless there is a burning question from one of you. A burning one, yes. It's no, so, okay, so, but feel free to contact our speaker just after the meeting, if just after the session, if you have any question. But I propose that we start our last presentation. It will be, the last presentation will be from Lufthansa. So our next speaker is Mr. Christian Most. He will discuss about how AI could support the optimization of operations. So I think it will be a quite interesting topic as well to finish this session about airspace and operational efficiency. So Christian Most is heading the development of decision support tools in Lufthansa Group's Operation Control Center as Senior Direct Digital Operations Optimization since April 2021. And before that, he was leading the executive board of Dr. Kaiser, Chief Operating Officer at Lufthansa Group. But now, I give you the floor for an operational presentation. Thank you.
Thank you for this kind introduction, Marilyn. Good afternoon, ladies and gentlemen. To catch up some time and to not repeat what was already said before, I will pretty much focus on our Lufthansa Group perspective on the several aspects when it comes to efficient operations. When I talk about the Lufthansa Group, this is more than just our airlines. It's not just Lufthansa Airlines. There are more airlines in Europe under this structure, up to digital companies and also our Lufthansa maintenance organization, Lufthansa Technics. We as an aviation company are well aware of what is our climate impact and what role do we play in the international context. Therefore, we have a very ambitious goal to reduce our carbon emissions by 2030 by 50% until 2050 to become fully carbon neutral. The three main levers you already heard probably the last day about, it's the new technologies, it's SAF, and it's operations in the end. New technology does not only account for new aircraft, but also enhancing existing technology, for example, by the AeroShark technology you may have heard of, applying a drag-reducing foil on the aircraft on the 777, previously started at Lufthansa Cargo and now is also introduced at Swiss International Airlines and Austrian Airlines. When we talk about sustainable aviation fuel, the most promising for an airline to produce it at scale or to receive it at scale is, of course, the PTL fuels. And when it comes to operations, and Andreas and Akbar already pointed a lot of things out there, It's not just the ATM procedures, it's also our airline procedures, like the single engine taxi and in and out. It has a lot to do with working with the people. So thanks for the question before, and how do we change behavior? It's training, it's inclusion in the development to gain trust. And it's also in how do we optimize our operations with digital tools. And this is where we'll come to in a second. The Lufthansa Group invests annually a double-digit million number into research, which is strongly supported by public funding, especially also the German LUFO projects. When we come to operation steering, and Akbar had some examples from the United States, we in Europe experienced as an airline, but also whole aviation industry, quite tremendous and terrific summers in 2017, 2018, where the growth of the overall industry just came to a point where it was too much to handle for the ecosystem. And for us, there was the major learning that we need to invest and to improve our steering when it comes to future impacts, and COVID just was the proof point in that term that we need to invest in this. We as a Lufthansa Group, and this is possibly true for the whole industry, and Andreas mentioned it already, technology optimism. We are quite good when it comes to training pilots, operating aircrafts, building aircrafts, and so on and so on. But when it comes to becoming more digital and handling data, there are probably stronger players out there, and that's why we decided actually to do partners. And in this area, in operation steering, we decided to partner with Google. The improvement that we are achieving, and this is a slide from 2019, and that this is still true. And I would like to highlight the last point, and this is to reduce the overall complexity. Why is complexity so difficult? Because we used to solve complexity in the past by splitting the problem into sub-problems. And this today in operation steering, if you imagine an airline like Lufthansa with 2 hubs in Frankfurt and Munich, usually has a certain way of finding solutions for a problem. And this is sequential solution finding, because there's no entity or system or human who actually oversees all dependencies. We have in the airline, and this is mostly true for all the airlines in the world, a classical split into aircraft steering, passenger steering, crew steering, and the maintenance department. And the sequential decision-making has a second challenge, and this is the speed until you come up with a good solution and the quality of the solution. To optimize this in the future, we integrated all existing data in a live environment into one cloud environment to actually be able to leverage the data that is existing today already, so we don't have a data problem, into one environment so we can actually work with it. And this is also true what Andreas mentioned already for Europe. This is the only way forward, and we as Lufthansa Group do our part to actually enable all of our airlines of the Lufthansa Group to work with these new technologies and to benefit from them. What are we actually doing? First of all, because we want to do this at scale for all of our airlines, we need to connect them into our cloud environment. The challenge with this is that the standardization also across our airlines when it comes to the legacy systems is not there where we would like to be. So the first step is pretty much a standardization, defining new operational data models to actually unify leg data, passenger data, crew data, and so on. In the second step, we need to teach the system how our hub and spoke system or our point-to-point carrier system actually works. And this is pretty much in the knowledge of the people. Usually an average ops controller at Lufthansa Airlines in Germany, for example, usually does this job for 20 to 25 years. And the knowledge that you're gaining in this time is invaluable. And it's badly documented. So what we are doing is we're sitting down together with developers, business analysts, and the actual experts to code the rules that they have in their mind into the system. So the system is actually able to support them in the decision-making by providing better solutions in a faster way. So actually quite similar to the ATM management, it's decision support. It's not about getting rid of people with everything that Akbar already mentioned. There will be change to jobs. There will be adaptations. There will be new systems. When we are then able to generate possible future scenarios for aircraft allocations, or in a major case, and this is our ultimate goal, to come to an integrated disruption management, we also need to evaluate these scenarios. And the evaluation today, when you think about optimization technologies, is often driven by average values. And we love our average values, for example, for delay minutes or cancellation costs. And let's say the delay minute is €50, and this number is always wrong. It's a good approximation, but it's always wrong. Sometimes it's 0, and sometimes it's 10,000. We don't care about the 80% who are 0, but we care about the 20 or 10% who are very high, and this is what we want to avoid in the future to improve our decision making. In the end, it comes down to technology to actually do this in a live environment, and we talk about to have steering decisions from less complex decisions, which we want to take in 3 minutes, up to major decisions, handling global disruptions, major irregularities by a snowstorm or a reduced ATC capacity in 15 minutes. So today we are handling between 3 to 5 terabyte of data every 15 minutes due to the sheer number of aircrafts that we're handling at Lufthansa Group, which is over 700. It's 250,000 passengers and O&Ds that we're serving every day, and up to 8,000 crew members in the air every minute. For the human, and this is really centric in this approach, we want to support them in their daily business. So it's not about that they then have to manually enter all the new changes into their systems. It's really about to support them with this, also to actually have a playground environment, a sandbox, where we display the alternative, where they also can manually interact and refine them, because the system, and this was also said today, is never perfect. The complexity in aviation is that high that a system can only come to a certain amount of accuracy, and then it's the human in the end with us creativity, curiosity, to actually make it a perfect solution and to execute it in the end. This is the basic approach that we are dealing with. When we optimize as a company, we are trying to optimize, of course, for our profit, but also for our customer satisfaction and for our crew satisfaction. And the challenge is to balance this. So during the day, during the year, there's a certain change in how do we optimize. So there is no one optimization function. There are different optimization functions, and they need to be calibrated by the human in each individual situation. And luckily, there's a strong correlation between becoming more efficient and becoming more sustainable, because the more we reduce our fuel burn, the less cost we have for our fuel, the more we also do for our planet. And one of the first tools that we did was actually to invest into a tail optimization technology, to actually then being able to integrate it with other optimizers for passenger management, for crew management, for maintenance management, and then have an overarching optimization with a disruption optimizer. This is a known problem to the industry and has been solved before, so that's not the new part. What is new in here is that we actually rely on a day-to-day fuel prediction, which is capable to predict each individual fuel burn of each individual aircraft every day. Because, you might know this, the fuel burn differs up to 10 to 12% versus the original deployment, and some changes you're not even recognizing. So the drag or the cleanliness of the hull has a certain impact. Of course, the main impact has the calibration of the flight management system, and the most impact has the engine. And what you can see here is then how the system actually works. It's not such a nice diagram that Richard and Christiane showed us before. It's the typical Gantt charts in the airline, and we love them. However, we try to get rid of them and to replace them with a little bit more visual representation of the actual world. You can see how the system proposes changes. The light red ones are the original plans. The dark red one is the new plan, and this is actually a screenshot from 2 days ago. This optimization is run every day at Swiss, where we introduced it first in 2021. And since the introduction, we were able to save over 10,000 tons of fuel only at Swiss, and over 12 million Swiss francs of variable costs, where the fuel is the biggest part in it. Now we are in the phase of scaling solutions like this and other solutions to our group airlines like Lufthansa and Eurowings, and probably next year also to Brussels Airlines. And we see a full potential for this type of fuel optimization up to 50,000 tons CO2 per year. It's a rather small optimization compared to what we have seen from Andreas, what is technically possible or feasible in the future when we're talking about ATM at scale. And we are only talking now about one airline, and this is only one tool. Just to give you an example how we believe that technology can enable us into becoming more cost efficient, but also more efficient for our environment. Because we heard something about contrails also, I would like to give you a perspective on our perspective on contrails. One important remark here is that a regulation of contrails, as we also see for SAF today in Europe, in our perspective, somehow neglects the global character of aviation. We need to be very careful when it comes to regulating this industry even further. And these are the 3 steps in our mind that we need to answer before we talk about regulation. First thing is the prediction. So in order to avoid contrails, we need to have a pretty good prediction model in place that actually gives us way ahead of a flight, ideally. So when we plan the trajectory in the dispatch system, an idea what is the area we need to actually avoid. So because the earlier we know that, we can actually plan around it, and the smoother it gets when it comes to the actual operations and managing capacities, for example, also for ATM providers. The second thing is that we need to think about avoidance. It's not just about the horizontal or lateral avoidance to fly around these critical areas. We also can have a look at, and the science already showed us some things that are ongoing about having different power settings in engines. How is the role of SAF in the future? How is the role of blend? Is there actually a mix, maybe the most beneficial when you fly in this area and switch then fueling modes? Everything is adding, of course, complexity, and complexity needs to be handled by technology. Otherwise, we won't be able to have these improvements. And then last but not least, and the previous talk touched it a little bit, if we need to have, or if you want to have a regulation on it, it needs to be quite a well sophisticated measuring and tracking method to actually have an accurate alignment on which aircraft did actually produce which contrail and how it is charged. And this is, from our perspective, still the most lacking part where the least work is done today. But it probably will be done in the future. Beyond this, we are also engaged in research when it comes to contrails with the German DCALT project, also with inclusions of the DLR and others. And I'm pretty sure there will be further research ongoing, which will be published next year, 2025. And Lufthansa Group will be part of this because we have a strong interest to see and to shape research also in this area to benefit from it in the future. To wrap it up, and this goes pretty much in the direction of the previous talks, we are now in the very early phase, and I say this after 3 years working in this project, really to optimize the steering of our airlines and to include whatever is coming there. We started as an airline with what we are today responsible for, but we know, of course, the whole ecosystem of airports, providers, and air traffic control that needs to be included in the future. Because today there are a lot of situations where we optimize against each other. Each player is optimizing itself ecosystem, and this is not leading to an overall optimum of the industry. So we need to change that. To make this in a very efficient way, we believe that we also need to come from an only steering or day of operations perspective already into a planning perspective where we can align capacities and demand in a better way. And also to include the learnings that we have from operations day by day on critical rotations, on critical flight times, on certain weather patterns that form in the past and will form in the future with the climate change, to include that as early as possible to relieve pressure from the actual system when it is produced, which will also benefit the customers with their journey and their customer satisfaction. And as we know, each disruption also usually causes more fuel burn than necessary. What is the key in our perspective to achieve that? This is what we call something like an industry cloud, where partners can share data, not telling any business secrets, but really share what is their priorities, what is their most accurate and up-to-date data on a certain information, like a lag, like a timestamp, like a prediction. So actually each player in the system can benefit from that, work with that, and actually push back their perspective. And this is to be seen in a real-time environment. And what I will do next is actually to look at Andreas' concept of the ATM master plan for the future, to see what they have in mind. So when there's a phase in 2025 to apply for these research topics, let's see if we find something that fits to our vision of the Lufthansa Group. Thank you very much for your time and for your listening. And with this, back to Marilyn.
Yeah, thank you, Christian. Are there any questions for Christian? Yes, I see a hand raised.
Thank you very much for the talk. Just a quick question from my standpoint. As you start incorporating your machine learning algorithms and you're connecting to existing data sources, what is your strategy for dealing with hallucinations that can be generated within that system? I guess as they are getting more and more connected with decision making, how are you kind of mitigating against those to try to reduce the likelihood of them?
Yeah, rather than trying to optimize the model for 3 years and then bring it out to production, we actually try to push it as early into production and deal with the feedback. So the agile development we are now in, and this is something we also had to learn what that means, and also the user needed to learn what that means, because they were used to 100% fixed and running systems when they are delivered. Now they are forced to give feedback in order to improve their work. And to establish an organization which is capable to deal that with producing fast solutions and then dealing with the feedback to improve the solutions is something that took us quite some time. We managed right now. And actually this is how we do. Try it out.
Thank you. I was going to ask a similar question actually. How are you challenging what the AI is proposing to you? Because I agree, it's the human who needs to validate it, but we know that the more we use AI and the more we have a tendency just to believe what it's telling us. And so how do you ensure that you are still challenging what's happening?
Yeah, it comes back down to the training of the people. I don't know how many years ago, but when you remember the first 747 cockpit, you need two pilots and 2 engineers to fly it. Right now, you're down to 2 pilots. Sometimes you extend it to 3 on a very long route, but you got rid of the engineers. And this was achieved by automation, by alerting, monitoring, to actually have an informed pilot still there. And they are trained today differently than they were trained 30 years ago. And this is true also for ops controllers. So the training changed. The way how select people for this job changed. You're not more like the frontline guy who first shoots and decides and then looks what happened like a James Bond. You're more like a Q in the future. You're monitoring a system, more like a dark cockpit logic, and rely on the system and then actually decide on an optimizer, a simulation. So what is the impact if I decide now this and that? And then decide, and then learn from this and actually include that back into the development. So it's this iterative approach and the combination of technology, human training, and procedures.
Okay. Any last question? I'm looking to the time. No, I have just maybe one last question for you, because you mentioned non-CO2 and contrails avoidance and dysregulation. And you said also that your AI should be done on a planning point of view. But when we speak about non-CO2 and contrails, because of the prediction, it's more at tactical level. And you know that it will jeopardize the stability of the network because we will lose predictability. So what is your view on that?
I think that technology will solve it. It's just a matter of time. When you look back into the first weather forecasting models or in the news, when you saw these 2D maps on how the wind and the temperatures will change, and you can imagine now that there are four-dimensional super Cray computer simulating each individual atom on a certain degree level. And by this, how much better our weather forecast is now than 20 years ago. And this is not a linear development, this is an exponential development. So I cannot tell you maybe there's already tomorrow someone who solved it, or maybe in 2 months, or maybe a year, but I'm very confident someone will solve it, and then we can actually move from the steering in the day of ops time frame more to a planning preventive optimization for the ease of all players.
Yeah, thank you, Christian. Big round of applause for you.
Thank you.
And this concludes this session. I would like to thank you for attending this session, this 2-hour session. It was a very interesting presentation. I would like to thank all our speakers as well. I have just a final message to convey, if I may. We have discussed this, but the air traffic management community needs more research. Every topic that has been mentioned, we need more research. And we need to accelerate, the deployment of those new technologies. So it's really a call to tell you that what you are doing is very important, and the ATM community is really pleased to work with the research community and also with Clean Aviation, because we will need, to integrate those new technologies, those new aircraft, hydrogen, hybrid, electric ones in the European ATM network. It will be quite challenging, and without innovation, without your studies, without the research, we will not make it. So we have to work all together on this. Thank you very much for attending, and enjoy the last part of the conference.